The mean value theorem. This theorem deals with an average value. That's what this word mean means. Average. It's not like how somebody can be mean by saying, your feet really are the worst smelling. No, it's not like that. It's more like, this has to do with the average rate of change. Average rate of change. I will abbreviate AROC. The average rate of change of a function f on the closed interval a to b is computed by f of b minus f of a all over b minus a. And again, that's how we find the average rate of change. So essentially what that means is that if you have a graph, in pictures anyway, if you have a graph that looks like this, and you pick up an interval from A to B, the average rate of change is simply the slope between these 2 points. So the slope of the secant line is the average rate of change. Again, a secant line is where a line crosses a graph more than once. And if it's a line, then we can find the slope of it. So there's your definition of average rate of change. And this is part of what the mean value theorem deals with. So let's take a look at what else the mean value theorem deals with. Instantaneous rate of change, or IROC. The instantaneous rate of change of a function f at a specific x value x equals c is f prime at that specific x value c. This is the instantaneous rate of change. And what does that mean? Well, you've had lots and lots and lots of practice with this. If you have some sort of function here, going left to right, of course, and you pick a point, just one point, maybe right there, at C, and you draw in your tangent line, like this, the slope of the tangent line equals the instantaneous rate of change. So what do we do with these two things? We need the average rate of change and the instantaneous rate of change to help understand what the mean value theorem tells us. Mean value theorem, which I will abbreviate MVT. Mean value theorem states if f is continuous on the closed interval AB and differentiable on the open interval AB, then there is at least one x value c on the open interval AB such that, and this is the equation that we use, that the average rate of change will equal the instantaneous rate of change. So in pictures, what that looks like, if you have some random graph going from A to B, and it has to be continuous on that interval A to B, so I'll start up here, and maybe I'll draw a graph that looks something like this, and it has to be differentiable on the open interval AB. Both of those are true with this graph. And if we look at the average rate of change, or we could say the mean rate of change between these 2 points, then somewhere on this graph, maybe about right here, we can find a tangent line that has the exact value of the average rate of change. So that's what this is telling us, that the slope between these two endpoints, or the slope of the secant line, will be the same somewhere in that interval as the slope of a tangent line. So it's telling us we can find the average value, but it is the slope of the tangent line instead of using 2 points, the 2 endpoints. One other thing that I want to mention here is that this theorem only tells us that a C exists, and it doesn't necessarily state how you find that C value. But we will go over that once we get into some examples. Example. Use the mean value theorem to find the values of C that satisfy this equation. And this is what is known as the conclusion of the mean value theorem. So here you're given a function and an interval. And so the first thing you want to do is find the left side of the equation over here. You want to find the average rate of change. So find the average rate of change. So what that means is you need to find f of 1. So you substitute 1 in for all these x's and you end up getting 2. And then you need to go through and find f of 0, and that gives you a -1. So this is what we would say is f of b, because over here in the interval, b is going to be the second number and a will be the first number, which means this one is f of a. So then we can just substitute these numbers into the formula. So we would have f of b minus f of a all over b minus a. So we have f of b is 2 minus f of a is -1 all over b is 1 and a is 0. So it looks like here we need 3. The average rate of change is 3. So the second step here is to find the derivative. So we have f of x equals x squared plus 2x minus 1. And if you use the power rule for all the terms here, you end up with f prime of x equaling 2x plus 2. So we found the average rate of change, 3. We found the derivative, 2x plus 2. And since we are trying to find a c value, the final step here is to set f prime of c equal to the average rate of change and solve for c. For c, okay. So what that means is that this is the derivative here for x, but since we are trying to find a specific value of x, c, I want to use this c variable. So f prime of c is simply, this is just a variable switch here, 2c plus 2 equals 3. So if you solve this for c, you will get that c equals 1/2. So there's your answer, 1/2. Let's take a look at what this means in pictures. So this is part of the graph for the function that was listed on the previous slide, the x squared plus 2x minus 1. And I've listed out a few ordered pairs here. There's one here. This one ends up being the vertex for the parabola. And then these 2 points are what the interval covers. So what we did was, well, first we checked for continuity and differentiability, and I did not say this on the last slide, but because the function is a polynomial, it will always be continuous on whatever interval you pick, and it will always be differentiable on the open interval. So if you're given a polynomial, the mean value theorem works, automatic. So that being said, what happened was we found that the average rate of change between 0 and 1, right here represented by the pink line, that was m equal 3. That was a slope of 3. And so what we did by the mean value theorem, since this is a continuous and differentiable function on this little interval, they're saying there's some number between 0 and 1 so that the slope of the tangent line will equal the slope of the secant line. We're given that. So when we did all of the computations, we figured it out that it was about right here, that the slope of the tangent line was equal to 3 when c equals 1/2. But we had to go through and find the derivative, because remember, the derivative is what gives you the slope of the tangent lines. And we wanted the slope of the tangent line to be equal to 3. So we went through and figured that out. That was 2c plus 2 equals 3. And when we solved for c, we got that c was 1/2. Pretend my graph is perfect. But hopefully this picture gives you an idea as to what this theorem does for us. On to the next example. Use the MVT to find the values of c that satisfy the conclusion of the MVT. So in this scenario, you're given the new function g of x equals x plus 1 over x on the interval 1/2 to 2. So let's go through, oh yes, checking continuity and differentiability here is important. So let's see here. Continuity is g of x continuous on the interval 1/2 to 2. And the answer here is yes. And that's because the one number that we are not allowed to use for x is 0. If you take the denominator and set it equal to 0, you get x equals 0. And that is not on the interval. So yeah, this function is continuous on the interval 1/2 to 2. For differentiability is g prime of x continuous on the interval, open interval, 1/2 to 2. Well, I'm going to jump just a little bit ahead here. Remember, the second step is to find g prime of x, and that will equal 1 minus 1 over x squared. And again, this is not continuous at x equals 0. And again, that 0 is not included in this interval. So, yes, the answer here is yes. So it is continuous on the closed interval and differentiable on the open interval. So we can use the mean value theorem. So we've already figured out what the derivative was over here. G prime of x is 1 minus 1 over x squared. And that means we have to come back here and do the first step, being find the average rate of change. And so you have to go through this whole process here. Let's see, we want to find f of a, and that is the same thing as saying f of 1/2. And if you substitute 1/2 into these x's here, you end up with 5/2, or 2.5. I generally like to use fractions for these. Then f of b equals f of 2, which is also 5/2. So what we are looking for essentially is the slope between a and b. So we can find f of b minus f of a all over b minus a. So that is 5 over 2 minus 5 over 2 over 2 minus 1/2, which is 0. So this is the average rate of change. We already know what the derivative is here. So the last step is to set f prime of c equal to the average rate of change and solve for c. This is what the g prime of c equals the average rate of change looks like. And when you solve for c, the first thing you're going to want to do here is multiply both sides by c squared, thereby getting this c out of the denominator. So that leaves you with c squared minus 1 equals 0. And if you solve this for c, you should get that c equals 1 and c equals -1. Now, one thing you'll want to keep in mind is that yes, both of these are answers. That's true. But only one of these answers is in the original interval. And that's this one. This one is not in the open interval 1/2 to 2. So the c value, again, needs to be on the open interval, not the closed interval. It cannot be one of the endpoints. So in this situation, the c value is 1. And I want to explain just a little bit more about this exercise on the next slide. The first thing I would like to mention over here is that if the interval contained 0, if you remember from the previous slide, x cannot be 0. This is where the discontinuity happens for the function g of x. So if the interval were -1 to 1, then the MVT would not apply. And that's because the function is not continuous on the interval. So even if it were 0 to 2, the same thing. The mean value theorem would not apply for either of these intervals because the function is not continuous when x equals 0. Another thing would be that, let's go back to the f of a and the f of b. Each of these values were 5 over 2, which gave us the average rate of change equal to 0. So if the average rate of change is 0, and we're looking for, essentially, we're looking for an x value where the slope of the tangent line is 0, right? Because the mean value theorem says we're trying to find a c so that the average rate of change equals the instantaneous rate of change. This was the slope of the tangent line. This was the slope of the secant line. So if the slope of the tangent line equals 0, then we are guaranteed, that means c is a critical value. And now we're guaranteed that on this interval, there's a maximum or a minimum possibly happening at that point. But more specifically, that c is a critical value. So that is something else. We didn't have to, we sort of, by luck, we're finding where the critical values were on that short interval. So just keep that in mind as you're going along. If you're using the mean value theorem and the endpoints have the same y value, your average rate of change is 0, and essentially you're just finding a critical value there. For this final example that has not been written yet, I'm going to reveal everything slowly in hopes that you will try this one on your own So I will wait about 10 seconds after I put the problem up here to start revealing any steps needed for this example. But the directions are all the same. We're trying to find the C value so that the conclusion of the mean value theorem is true. So here's the function. All right, so here is the entire example worked out. We check that h of x is continuous on 1 to 3, and yes, it is. And this is not a polynomial, this is a square root function. So if you want to see where this function even exists, you can take the radicand, or that which is on the inside of the radical, and you can set it so x minus 1 is bigger than or equal to 0. And we set it to be bigger than or equal to 0 because you have to take the square root of a number that's 0 or bigger. And when you solve for this, you can find that the domain here is, let's see, as long as x is greater than or equal to 1. So this function does in fact exist on this interval. And if it exists on this interval, then it is continuous on that interval. So square root functions are continuous over their entire domain. So yes, this is continuous there. But h of for differentiability, is h of x differentiable on the open interval? That's the same question as asking if h prime of x is continuous on the open interval. And you might be looking over here where the derivative is and saying, well, hey, you know what? This, when you set this denominator equal to 0 and solve for x, you get x cannot be equal to 1. And you're right. If you substitute 1 in here for x, then you will end up with an undefined value. You end up with a 0 in the denominator. But if you come back and look at this interval for differentiability, we do not include the endpoint, right? It has to be differentiable on that interval except at the endpoints. And so this value is an endpoint value. And so we don't count that. So yes, even though the derivative is not continuous at 1, we are not including 1 in that interval. So then we can go through then and set, and I realize now all of these should be C's, so this should not be X, this should be C all the way through. So with that tiny little mistake that these should be C's, I think that's the only thing that is incorrect on this slide. Yeah, it looks like it. So apologies in advance. These all down here in step 3 should be C's. The final answer should be C is 3 over 2. And look at that. 3 over 2 is in fact on this interval.